Let's take a minute and talk about light. Light by itself is not of primary interest to us as chemists, but by looking at how light interacts with matter, we can learn something about the nature of light itself and also about the nature of the matter. Light is considered an oscillating electromagnetic wave. Now that sounds all very complicated, but light itself can be more easily defined if we stop and look at it in a couple specific ways. You may not be able to picture the electromagnetic part of it, but if you think of a wave the same way you think of a wave in water, it's the same basic thing except it's electromagnetic fields that are moving instead of water. But all waves can be defined relative to the same basic properties, and so we want to look at this electromagnetic wave two different ways. I'm going to freeze the wave and then walk along beside it, or I'm just going to stand still and watch the wave go by. And I see the same thing but in two different ways. So if I freeze the wave and walk by it, the wave just stays there as I gradually move across the wave. And so if that handsome gray-haired gentleman, who's not me, right, is looking, well, what does he see? What he sees is the waves going up and down in his window. So his vision is this little window. Here he sees this high little peak. Down here he sees this low little valley. Right? So if you think of the wave as an actual thing that can be seen, what he sees is something that's going up and down. And it keeps going back up to the same point, or if you prefer, it keeps going down to the same point. So one way to actually define this wave is to talk about how far he had to walk before he saw it reach the peak again. Or again, correspondingly, he could look at how far he had to walk to see it reach the bottom again. So this distance he walked is a length. For a wave, it's called the wavelength. It's quite literally the spatial length of the wave between corresponding positions, either the highest points or the lowest points, or frankly pick any two identical points in between. The wavelength is usually abbreviated by a Greek letter lambda, and it's simply measured in units of length. Any unit of length, miles, meters, feet. Obviously, SI units would have it in meters. Okay. The alternative way to look at it is for me to sit still and let the wave go by me. So now if I'm looking in this little window, well, what do I see? What I see is the wave go up and the wave come down and then up and then down and then up and then down. Now I'm not moving, so there's no distance here, but what there is an up and down motion in my window as a function of time. So it goes up in a certain amount of time and it comes down in a certain amount of time. The number of times it goes up and down in a second, again, SI unit of time is second. I could use minutes or hours or days or years, but generally electromagnetic waves are pretty fast, so seconds, right, works fine. The number of times it goes up or down in a second is called the frequency of light. Again, same wave, just visualized a different way. Right? This frequency is abbreviated by the Greek letter nu. It's a Greek n, and it simply has units of reciprocal time. It's really the number of waves that go by in a unit of time. Okay? The wavelength and frequency are related. Right? They both apply to the same thing, this electromagnetic wave, and so they have to somehow be related. And you know, I like to say it, units, units, units. If I look at the units of the two, I can kind of see what the relationship's going to be. The length of the wave is going to be measured in meters. The frequency is going to be measured in reciprocal time, 1 over seconds, if I combine the two, I get a distance per unit time. And if you think back to physics, right, distance per time is a velocity or a speed. It's the distance traveled by the wave in a period of time. And again, any units for distance or units of time will work. Miles per hour, meters per second, kilometers per day. In SI units, again, the preferred unit would be meters per second, since meters is the SI unit of distance and seconds is the SI unit of time. Right? And so we can actually combine these three wave properties into one algebraic relationship. The wavelength, again measured in some unit of time like meters, the frequency measured in units like reciprocal seconds, combine to give me a speed which is measured in meters per second, distance per time. And it turns out that the speed of light in a vacuum is actually universally constant. It's 2.997 times 10 to the 8th meters per second, or if you don't need 4 or more sig figs, 3 times 10 to the 8th meters per second. We don't need to dwell too much on this now, although we will talk a little bit later about how matter and light interact, but this is only a constant value in vacuum, because if you actually introduce molecules, the light interacts with the molecules and it actually slows down. You know, I've said here that the light bumps into the molecules. That's not 100% physically accurate, because it's actually an electromagnetic interaction more than actually bumping, but you know, it's easy to visualize as a bump, right? So if my light is passing through an actual material where there's molecules, its velocity is not c, right? But in a vacuum, or even in air where there are very few molecules, it's a reasonably constant value of, again, 3.00 times 10 to the 8th meters per second. And so I can define my light two different ways, right? I can talk about its frequency, number of waves per second that passes by, or I could talk about the length of a single wave, the distance between two peaks. But they're interchangeable, right? So if I have a wavelength, say 600 nanometers, that's one way to define the light, and 600 nanometer light actually is orange, right? I could also define orange light in terms of the frequency, because in vacuum or air, right, 3 times 10 to the 8th meters per second is the product of the wavelength and the frequency of the light. Now I do have to be a little careful about units here. This is nanometers. If you don't recall, a nano is 10 to the minus 9th. Right, so 600 nanometers is 600 times 10 to the minus 9th meters. Right, but as long as I'm careful to make sure my unit's correct, I can use my wavelength measured in meters to give me a frequency measured in reciprocal seconds. So again, in vacuum or air, the speed of light is 3 times 10 to the 8th meters per second. That has to equal the wavelength times the frequency. And in this particular case, I calculate a frequency of 5 times 10 to the 14th per second. You'll notice this is a relatively big number. For orange light, if you sit there and sort of stare at the orange light bulb in your room, if you happen to have an orange light bulb in your room, the orange light that's going by, right, there's 5 times 10 to the 14th waves passing by every second. Okay, that's roughly 500 trillion, roughly. It's exactly. Light is very fast moving and oscillating very rapidly. Now, reciprocal seconds is sometimes written instead as a hertz, abbreviated Hz after the scientist. So 5 times 10 to the 14th per second is also 5 times 10 to the 14th hertz. And so either the frequency or the wavelength can be used to define the wave of light, and when we're talking about actual visible light, it's also telling us what the color is. All orange light has a specific wavelength, and 600 nanometer light is orange. We'll talk later about how this light interacts with matter and what it tells us about the matter itself, and frankly what that interaction tells us about the light. The most important thing really to take away from this when it comes to matter and light is that light is just another form of energy. Right? You can heat something up by putting thermal energy into it. You can heat something up by putting kinetic energy into it. You can also increase the energy of a system by putting light into it. But we'll talk more about that in the next presentation.